problem. Maya is driving down the road when she spots a squirrel 55 meters in front of her. I do that squirrel 15 times trying to get it right, and I absolutely cannot. So, anyways, here I am, and I'm 55 meters, not miles, 55 meters in front of this poor squirrel when I notice it, and I suddenly decide to hit the brakes. Except it doesn't happen suddenly. It takes me, as the problem says, zero point 0.8 seconds to react. While I'm reacting, what's happening to my car? My car is still moving at the speed it was moving originally. So there's kind of two phases to this problem. There's the reacting part of it, where I'm reacting, and there's the stopping part, or let's call it the braking. Let's assume the best for the squirrel and assume that I stop in front of it. But here we have the braking phase, and the whole thing comes together to make the stopping. So there's different kind of motion in both of these phases. The problem tells us that I'm traveling at 25 meters per second at the start of this problem. So 25 meters per second is my initial velocity. I'm still going 25 meters per second when my foot first touches the brakes. So I've already traveled this distance. Let's just say this is I don't know, I can call it delta x1. It's my initial distance. I'm still traveling 25 meters per second, right? But when I stop eventually, my final velocity will be 0 because I'm going to come to rest, hopefully in front of the squirrel, but we'll let the problem dictate that. And the amount of distance it takes me to brake, I'm not braking, I'm braking. Braking. The amount of distance it takes me to brake, we can call that delta x2. Delta x2. And we know that if this is going to all work out, it's going to be that these two numbers added together should be less than 55. So one of the things that's tricky is knowing what information to use and when. Setting up your problem is super important. We're not actually going to use this 55 until the very end when we compare our distance to the final to that 55 meters. So let's break this up into two parts. During the reacting phase, we have a constant speed, constant v, right? And so what that means is I can describe my motion fully by only three variables, delta x, delta t, and v. Because if you think about it, v equals v naught is equal to v, and a is just equal to 0. So we don't even need these three things. It's like those three things are not important. In other words, the average the average velocity is equal to the instantaneous velocity throughout this whole interval. We know this is 25 meters per second. We know, we don't know this, but we know that it takes 0.8 seconds for me to react before I realize that there's a squirrel on the road in front of me. So we can use the average acceleration or the average velocity or the constant velocity equation, which is just delta x equals v delta t. This is just your d equals rt equation that you're used to in math. And we can plug in the numbers, 25 times 0.8, and we get 20. 20 meters is how far I travel while reacting. So we can call that delta x1, right? We're going to call that delta x1. Now let's look at the braking part of it. Braking. Hopefully not braking. This one, we're accelerating now, right? Accelerating. So we're going to have to go to all of our equations, delta x2, delta t, v naught, v, and a. So it gives us some information here. It tells us that the rate of acceleration is 9.3 meters per second squared. Think about what that means. It says rate of deceleration. So we're traveling in the forward direction. What that means is each second that goes by, the brakes are taking away 9.3 meters per second of speed each second. So each second I'm going 9.3 meters per second slower until finally I come to rest. So it's important to understand at this point that the acceleration is actually backwards because you're subtracting. It's going to be in the backwards direction. And remember, the way we define directions is by a positive and a negative. I could make backwards the negative direction and forwards, the positive direction. So when I plug my acceleration into this equation, it's going to be negative 9.3 meters per second squared. I'm assuming my final velocity is 0. I know my initial velocity is 25 meters per second, and so now I can use this information to calculate the braking distance. How long it takes, I don't really care. It's my don't know, don't care, because it's not relevant to this problem. So then, using the equation without delta t, I get v equals v naught plus a, nope, that's the wrong one. It's v naught squared, v squared equals v naught plus 2a delta x. So we're going to rearrange this and solve. Delta x equals v squared minus v naught squared over 2a. And when I plug in the numbers here, I get v, which is 0, subtract 25 squared all over 2 times negative 9.3. And when I solve that, I'm going to do it quickly. Divided by 2 divided by negative 9.3, I get 33.6. So the negative divided by the negative becomes positive 33.6 meters. Does that positive make sense? Yes, it does. What it's saying is, as you are slowing down, your velocity is decreasing, you're decelerating, but you're still moving forward. You're moving forward 33.6 meters. So now we can put this all together. Stopping distance, stopping delta x is equal to 20 plus 30, this is not right, 33.6, oh it is, it equals 53.6 meters. Since this is less than the distance, I can definitely say the squirrel lives.